Hello everyone, welcome to my YouTube channel. My name is Kamran, and in this video I'm going to talk about a smart car parking system by using the fog computing. So previously I published a research which is titled as Towards a Fog Enabled Efficient Car Parking Architecture, and I simulated the whole scenario by using the iFogSim. So in this video, first of all, I will discuss that published research with you, and later on I will talk about the code that I developed or write using the iFogSim toolkit. So without any further ado, let's jump into my computer and first discuss the smart car parking architecture. Alright, so now let's select this paper, Towards a Fog Enabled Efficient Car Parking Architecture, and as you can see that it name depicts like this whole car parking architecture is all about the fog computing, and the efficiency and the effectiveness of all this car parking architecture is due to the fog computing. Because in the previous video, in IoT video, I discussed with you that there are some couple of potential problems with the cloud computing, that when you send the large amount of the data, it is there is latency problem, there is network usage problem. So to solve all these problems, we have used the fog nodes in our car parking architecture. And this is the normal structure of the paper, as we have the abstract, introduction, background. So I'm just going to the particular part which is very important to discuss, and that is this one. So this is the 3-tier architecture for the fog enabled smart car parking architecture. So the whole idea of this research is that we have a parking lots, and in the parking lots we have deployed the multiple smart cameras which take the pictures from the parking lots, and they are connected with the microcontroller. So whenever they capture the pictures, they transmit or they transfer the pictures to the fog node. On the fog node, we have deployed the image processing algorithm, which is used to identify the parking slots which are vacant or which are not occupied. So here you can see that in tier 1 we just have cameras. In the tier 2 we have fog nodes, and the cameras are connected with the fog nodes through the microcontroller device. Then this is a proxy server, or you can say that it is a gateway device, and through the gateway device we are connecting our fog nodes with the cloud server. So as I explained previously, in the previous video, that fog computing is not here to replace the cloud computing, but it is just extension of the cloud computing. And the fog is also a cloud which is very near to the user or your IoT device, right? So the fog nodes cannot exist without the cloud node. So this tier 2, when we introduce the fog nodes here, makes your architecture more efficient and effective. So if I replace these fog nodes and I directly connect the cameras with the cloud server, and now if you imagine there are multiple parking areas, and all the cameras in all these parking areas, they send their pictures for processing to the cloud server, right? So in this case, there will be a lot of requests to process for a cloud server, which will ultimately increase the latency time and the network bandwidth usage. So this is the whole architecture, right? And what I did, and let me just show you one more thing, and it is the architecture for multiple parking areas. I assume that this is parking area 1, and then we have multiple parking areas like parking areas N. So for every parking area we have a separate fog node. So for example, if we have 10 parking areas, we have 10 fog nodes, one fog node per parking area, right? And then in order to evaluate the effectiveness of this architecture, what I did, I created 2 scenarios in iFogSim. The one was using the cloud computing, and the other scenario was using the fog computing, right? So I got the results of latency and network usage, then I compared the results, and ultimately I found out that when you use the fog computing in the tier 2 or middle tier, then your latency rate and the network bandwidth usage is significantly come when you directly connect your cameras to the cloud server. Alright, so this is the topology. So here you can see that the C1, C2, C3 and C4 are my cameras which are connected to the fog node, and then the fog node is connected to the proxy server, and then the proxy server is connected to the cloud. And similarly, this is my LED 1. The idea is that when we process the parking slots, when we get the status of every parking slot, then we update the information on the LED which is presented on the entrance of the parking area. And one more thing that I wanted to incorporate in this research was it should not depend on any Android based application or your smartphone application. So for example, if a driver he does not use or she does not use the smartphone application, then they can use this system, right? Because all the information of the parking is presented on the main gate of your parking area. So that was the motivation. And similarly, we have multiple cameras with different fog nodes, and these are the parameters of my fog, proxy and cloud server. So when I will go to the iFogSim toolkit, I will explain it to you there. And this is my topology for cloud server. So when we don't have the fog nodes, we are connecting all the cameras and LEDs with a cloud node, and we are processing all our data. So this is a very important table that we can discuss, and these are the simulation results for the proposed car parking architecture for fog and cloud. So now you know that I simulated two scenarios. One was for the cloud and second was for the fog. So when I was considering cloud, I connected all the cameras directly to the cloud and got the results. And when I got the scenario of fog, I implemented the fog in the middle tier, connected my cameras with the fog node, and I got the results. So when I have the 16 cameras, this is the latency in milliseconds, this is the latency for cloud in milliseconds, and this is the network usage in kilobytes, and this is the cloud network usage in kilobytes. So here you can see that when I connect the 32 cameras with the fog nodes, the latency is 9.30 millisecond for processing all the pictures and displaying the result on the LED. But in case of cloud, it is 292.6 milliseconds, and that is a significant difference, right? So that's why and here you can see that this is the network usage, and for fog, and there is a huge difference between the network usage of fog and cloud. So, and here you can see that when I attach the 48 cameras with the fog nodes, the latency is 10.73 for processing all the pictures and displaying the result on the LED, and on the other hand for the cloud it is much higher, right? So this is the whole phenomena that I implemented, and I proved that when you use the fog nodes in the smart parking architecture, then the system is more efficient than the cloud computing. And then these are the graphs, and I will put the link of this paper in the description of this video. So if you want to give it a read, then you can open up that link and you can read this paper. Alright, so now I have opened up the Eclipse, and I have opened up the iFogSim. So if you don't know that how to set up the iFogSim using Eclipse, then I will provide the link of that video in the description of this video. So you can just open up the link and then you can set up the iFogSim using Eclipse. Although there are many simulators available for computing, but iFogSim is widely used by researchers and in the industry for the simulation of fog scenarios. So this is the reason that we are discussing the iFogSim right now. So once you have opened up your iFogSim, if you go into this particular package, you will see some of the built-in case studies there, and we will discuss these case studies one by one in the upcoming videos. But right now our focus is the smart parking using the fog computing. So I will choose the multiple methods which are built in iFogSim. So first of all, I have just created a simple class and I have imported all these required libraries. So what I did, there are three case studies which are built in. The one is DCNSFog, the other is 2apps.java, and VRGameFog. So I opened up the DCNSFog class, and then I copy all these required libraries into my smart car parking fog class. Okay, and then this is my class, and here I have a list of fog devices, and it is an array list which is dynamic. So basically in this whole scenario I will create multiple fog devices, so I will store all these fog devices into that list. So again, this is very easy if you just go to this class. So I have just copied it from here, so you don't have to write it, you just see the case study and copy the things from there. And then there is another list for sensors, because we will create the sensors here in our simulation. And then it is actuator list. Everything which is used to display the output is actuator in iFogSim. So for example, in my case the LED is actuator, and then it is an integer number for the number of areas. So for example, if I say number of areas is equal to 5, it means that I want to create the 5 fog nodes, 5 parking slots, and 1 fog node for each parking slot, and I want to connect 10 cameras with each parking slot. So now the total number of cameras in this scenario will be 50, because number of areas are 5 and number of cameras per area is 10. So 5 multiplied by 10 is simply 50, right? And then it is the camera transmission time, which is 5. So I assume that my cameras take the pictures like after every 5 seconds. And then there is a static boolean cloud variable. So when it is false, it means that I am about to send all the data to the fog servers instead of cloud. So if I make it, for example, true, it means that I will send all the data to the cloud server. Okay, so that is the idea. And then I have a simply main method, and this is like a line that I am printing on my console, that's starting the smart parking system. And all these lines, they are built in. I have just copied it from here. And then there is one other concept that is very important in iFogSim, and which is about the modules. In iFogSim you create module is basically a processing machine. So for example, I have one fog node, and in every fog node I can create multiple modules. A module is a virtual machine which is dedicated to perform a simple task or one task. So for example, I say that, like in my fog device there is a module whose name is slot detector, and I have placed this module on all those fog nodes whose names start with A, right? So what this for loop is doing, in this for loop I am just getting the name of my devices, and if the device dot get name dot start with A, it means that if that fog node is related to area or its name start with A, then I have to add module which is slot detector on my that particular fog node. So this is one type of virtual machine which I have created on my fog device. And if I talk about this, so now in my case the cameras are also device, because they are doing some computations, right? I have embedded some module into that embedded module which is responsible to capture the pictures after every 5 seconds. So in iFogSim there is a concept that every computational device is known as fog device. So either your cloud server is also a fog device. So whenever you will create a cloud server in your iFogSim, you will create it as a fog device. And similarly, I will create cameras as a fog device, because these are the computational devices, and this is a very important point to remember. So now I see that all these devices which start with C I have to put the picture capture module on that. So picture capture module is going to be implemented on my cameras. And okay, so this is the important concept. I have an if condition. It means that if the cloud is equal to true, our implementation is about cloud, or we want to send all the data to the cloud, then we have to add these two modules on the cloud devices. Now this is the object of the controller class, and controller class is responsible for simulating your whole scenario. So what we pass the fog devices, our sensor, actuators, everything to the controller class, and the simulation is performed there. And now let's discuss this thing. There is a built-in method in iFogSim whose name is create fog device, and it is used to create the fog devices. Now our hierarchy is like this. So this is our hierarchy, right? First of all, we have to create cloud server, then we have to create the proxy server, we have to connect the proxy server with cloud, then we have to create the fog nodes, we have to connect the fog nodes with our proxy server, then we have to connect the create the cameras and connect the cameras with the fog nodes. So now let's go back to my Eclipse, and here I'm just first of all creating the cloud device, because first of all I have to create the cloud device and I have to follow that hierarchy. Okay, so as I described earlier, that every computational or storage device in iFogSim is considered as a fog device and can be created by using the fog device class. So fog device cloud, which is equal to create fog device, and this is the name of my fog device, which is cloud. Okay, so this is the list of parameters that you have to pass. So first of all, you have to pass the node name, then you have to pass the number of MIPS, then what should be the RAM, and upload bandwidth, download bandwidth of your device, and here is the level or hierarchy level of the device. So in this case it is 0 because it is the cloud device which is on the top, so the hierarchy level is 0. And then we have to write here the rate per MIPS, busy power, idle power, and you can just copy the value of these parameters from the built-in case studies of iFogSim. Okay, so now we have created the cloud device, and its parent ID is -1, because for cloud we don't have any parent, rather than the cloud is parent of other devices. And after that we have added our cloud device into our list of fog devices. And next we are similarly creating the proxy server, and here the level of proxy server is 1 because 0 is on the top cloud server. Then we have level 1, which is proxy server, and similarly we are adding it into our fog devices, and we are setting up the link latency time. So this is the latency of connection between the proxy server and cloud, and I assume that it is 100 milliseconds. And after that I have to create multiple fog nodes, and it depends on my value of number of areas, which is equal to 5. So therefore I have a for loop here, and which runs which is less than number of areas, so it will create the 5 fog devices, and it call this method add area. So when we come into this method, we create a fog device for every area, and here we define the parameters. So in this case, in the case of fog device, now you can see that the level or hierarchy of fog device is 2, because 0 cloud, 1 proxy, and 2 fog node. And then this method will call exactly equal to the number of areas. So for example it is 5, so it will be called for 5 times, and then it will create the 5 fog devices, and all the fog devices will be added there. And the setup link latency between your proxy server and your fog node area, fog node is 2 milliseconds, I assume that. And then we have to create the number of cameras per area. So inside this method I have called the I am creating the cameras, and I'm calling a method that is add camera. So this add camera method is basically will be called exactly equal to the number of your this variable. So for example, when the first time you create a fork node, you attach 10 cameras with that, and then you create another fork node, attach 10 cameras with that. And here you can see that the hierarchy of this is 3, and we are embedding our sensor into that camera. So whenever you have to create a sensor, you have to use the sensor class, and whenever you have to create an actuator, you have to use the actuator class. Okay, and similarly the sensor is being embedded into the camera, and then the gateway device for my LED is fork node, because the LED will be connected to the fork node. So this is how I have created the cameras and the fork nodes, and this is then again a built-in function. I don't need to discuss about that. And then it is a very very important function in iFogSim, which is about to create your application. So here I have created an object of application, and in create application I have to add my app modules. So previously, as I discussed in the main function, we have 2 modules, so we are basically creating these modules here. The one is picture capture, and this is the value of the RAM for that particular module, which is 10. And similarly, this is the slot detector module, which will be embedded on my fork devices, and the value of RAM is 10 for that as well. So now we have to create the connections between our fork devices and our modules. Okay, so for that purpose we use add app edge function. It first take the source. The source is camera, and the destination is the picture capture module, because we have to start from the camera and then we have to capture the pictures. And this is the tuple CPU length, in which the tuples are basically the computational entities in your iFogSim, and then it is the tuple NW length, and the tuples that will be created in result of when the picture capture module work, I say it would be camera. Okay, because it would be kind of pictures. And then the direction of this camera is up, and this is a sensor. And next I am creating an other app edge, and here I have the picture capture module. So right now I have like you can assume that I have captured the pictures, and now I have transmit that pictures to the fork node for slot detection. So from the picture capture module, now I will send my data to the slot detector. This is the value of tuple, and all the output entity in this whole process, when the picture captured pictures will be sent to the slot detector. So as a output we will get slots, and this connection is between module to module. So that's why I have written here app edge dot module. So once these slots are detected, now I have to show it to my LED, which is my output. So now from the slot detector I am going to the PTZ control, which is my LED, and in that case I will get this output, and this app edge is about actuator. Okay, so these are the app edges that I have created inside my iFogSim class. So now we have to map the tuples. As I said earlier, the tuple are basically the entities. So from the picture capture module I will get the camera. So this is my picture capture module. The input tuple type to that module would be camera, and the output tuple type would be slots. And similarly for the slot detector, the input would be slots, and then output will be displayed on the LED, right? So after that I have to create the app loop. The app loop is used to determine the latency and network bandwidth usage. So app loop 1, and in which I am adding camera picture capture, slot detector, and PTZ control. So this app loop will basically compute the latency for initializing the camera, for capturing the picture, for detecting the slot, and sending it to the LED. And I am adding this loop into my list of loops, and then I have set the loops. And if I run my program, so now you can see that the simulation is in work. So okay, it would take some time. So what I'm going to do, I am just going to add number of areas 1 and 2 number of cameras per area, so that we can get the result very soon, right? Okay, so here you can see that from taking up the picture and from slot detection to PTZ control, this is my latency time, and this is the total energy consumed to your network bandwidth. So I hope I have delivered this concept to you. I know that it is very hard to understand if you are working on iFogSim for the first time, but still you have got the opportunity to write down your queries into the comment section. And if you don't understand anything in this video, just put it write down it into the comment. I will get back to you. I will provide you the solution, or you can directly contact with me. I can explain all these things to you, right, in detail. So just write down your queries in the comment section, and if you have any problem, I will try to solve it, and I would be happy to help you out. So thank you so much for watching this video. If you really like this video, then give it a thumbs up, and if you are new to my channel, then don't forget to subscribe it. See you in the next video. Thank you.